Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, please consider subscribing because you're in the right spot. That said, let's get into the current video. I'm going to talk about series solutions near an ordinary point for a differential equation. More specifically, in this video, I'm going to look at a second order linear homogeneous differential equation, but the idea works if this is non-homogeneous or a higher order. I'll do additional exercises in subsequent videos, but as you will see, the solution takes a bit of work. So rather than making this video an hour long, I'm going to do one example per video. Let's go ahead and get into this example. So solution. Now, when I say a series solution, what I'm going to do is I'm going to have a power series, and in this particular example, I'm going to do a series solution near x equal to 0. 0 is certainly an ordinary point of this differential equation, and therefore the solution that I'm going to look for is going to be a power series centered at 0, meaning it's going to have the following form. Y is equal to the sum n equals 0 to infinity, a sub n, x to the n. So that's a power series centered at 0. Now, of course, what's unknown for this series is the coefficients. Here's the idea. I'm going to take this series, I'm going to plug it into the differential equation, and I'm going to do some algebra to come up with a formula that gives me the coefficients. Here's how this works. First derivative would be the sum n equal to 0 to infinity, just using the power rule on this series. Okay, I get the expression n a n x to the n minus 1. Notice when I plug 0 into this, the very first term of the series would be 0. What I'm therefore going to do is drop the initial index term, giving me the sum from 1 to infinity of n a n x to the n minus 1. Now these two, of course, are the same. They represent the same thing, but since the very first term is 0, I'm going to drop that term off. Then, of course, for the differential equation, I need the second derivative, so I'm going to go ahead and differentiate again. Y double prime would be the sum from 1 to infinity. Using the power rule a second time, I get the following series. Now, once again, notice when I plug in 1 that the first term is 0. Therefore, I'm going to drop off the first term and start the series at 2, giving me the following expression. Now, what I need to do is plug in these series into the differential equation. Now, of course, if I had a first derivative here, then I would plug in all three of those, the unknown function, the series for the unknown function, the series for the first derivative, second derivative. In this particular case, I only need to plug in, of course, the series for the unknown function and the series for the second derivative. Let's go ahead and do that. Okay, so I plug that in. I'm going to get the sum 2 to infinity n minus 1 and x to the n minus 2 plus, and then the original function or the unknown function. Okay, and we get this. Now here's my goal, as I'm going to combine both of these into a single series. Once I do that, I'll go through the idea of how to come up with the coefficients, but first and foremost, I have to combine these into a single series. Now, once I do combine them into a single series, I would like to factor out the x to a power. Okay, so what I need to do first and foremost to combine them into a single series is the indexes must match. The initial index and the final index must match. Of course, they're both going to go off to infinity. That's not going to change. But what I do have to make match is this series starts at 2, this series starts at 0. Now, there are two different ways that I could accomplish that. I could write the first, so the n equal to 0 and the n equal to 1 term here off separately, and then start this series at 2, then they would both start at 2, then I could have the same summation, and I could combine those two expressions. The problem with that is that I would have x to the n minus 2 here, and then here I would have x to the n. Therefore, my first task is to make the I'm going to modify the expressions first before I potentially pull off any terms. Well, this is x to the n, this is x to the n minus 2, so I do have to do some sort of shifting in order to make those exponents match. Now, if I was to drop the exponent here, say I drop it down 2, then this would shift up 2, but then I would have terms like I might have, say, like negative subscripts, and I don't want to have that. Now, the way I'll do this is I'm going to shift the index here. If you remember, if I take the index variable, so index variable, and I increase it, then what happens is the initial index value must decrease, and they have to increase and decrease by the same amount. Well, if I want this to match x to the n, I'm going to make the index variable shift up 2 units, which means that the initial index value has to shift down 2 units. And notice that does accomplish both things. I'm going to get this to be x to the n, and I'll also get this to be n equal to 0. Let's go ahead and do that. This gives me, I'll use the same color here, the sum from n equals 0 to infinity. Now remember, when I increase the index variable, every single occurrence of that index variable is now going to get replaced with n plus 2. That means that this n becomes, of course, n plus 2. Here, this n would be n plus 2 minus 1, which would be n plus 1. The subscript on the coefficient here, this would also become a n plus 2. And then n minus 2 would become n, because n would become n plus 2. n plus 2 minus 2 would be x to the n. This series we did not manipulate, so it stays the same. Okay. And now again, I have both things that I was looking for. The powers on x match and the initial index values match. If at this step the exponents on x matched, but these did not match, then what I would do is, like, say this started at n equal to 1, I would pull off the 0 term to make those match and then combine them into a single series. Okay, so now I can go ahead and write this as one summation. And also, within that summation, I'm going to factor out x to the n. What I have then for the coefficient within this summation would be n plus 2, n plus 1, an plus 2, plus an, right? That's the expression for the coefficient within this series, and then x to the n is equal to 0. Now, the idea is that this whole summation is identically equal to 0. Well, that can only happen if this is identically equal to 0 for every single value of n. That then gives me an equation for the coefficients, and this is actually going to be a recursion relation between the coefficients. So let's go ahead and write that over on the other side. What that tells me then is I have n plus 2, n plus 1, an plus 2 plus an is equal to 0. Now notice what I could do is I could take that equation and solve for an plus 2, and I get my recursion relation. An plus 2 is negative an over n plus 2 times n plus 1. Well, in order to use this recursion relation, in order to solve for the coefficients, we have to start somewhere. So like, let's say I happen to know a1, for example. Let's say I happen to know the a1 coefficient. Maybe it's 4, whatever the case may be. Using this, if I know a1, I could generate the coefficient that's 2 terms later, so A3. But then knowing A3, I can get A5. Knowing A5, I can get A7. What you can see is that if I know A1, I can get all the odd terms. If I know A0, then I can generate A2. If I know A2, I can get A4. If I know A4, I can get A6. In other words, if I know A0, then I can generate all the even terms. What that tells me is I then have to break this into 2 separate cases. N is even, N is odd. Let's do the N equal to N is odd first. So N odd. Again, I have to have some sort of a starting value. And so what I'm going to do is I'm going to say A0 is not equal to 0. Of course, if that was 0, if A0 was 0, then A2 is 0, A4 is 0, and that doesn't really, which would give us a solution to the differential equation, but it's sort of the degenerate case, not very interesting. So in order to get the non-zero solutions, I'm going to assume that it's non-zero. Let's go ahead then and let's solve for the coefficients. Let's see if we can come up with a pattern for this. Okay, so I have A0. Now what I want to do is come up with A2. So A2 is equal to, now if I look at this, match this term up with the general equation up top here, notice that my subscript is 2. That means that in this case, n would be equal to 0, so it's off to the side here. Just as a reminder, I'm using n equal to 0. That means this would be negative A0 over, well, n is 0, so that'd be 2 times 1. Of course, that's equal to 2, but I'm going to leave it as 2 times 1 just because I want to see all the details so I can come up with a pattern. All right, once I have A2, we can now come up with, say, A4. If I match the subscript here with the subscript in the recursion relation, notice that this means that n would be equal to 2, because 4 would be n plus 2, so therefore, within the other side, n would be 2. And that should make sense, because in order to get A4, I have to use the term that's 2 previous, which would, of course, be A2. And I get negative A2 over, well, if n is 2, that'd be 4 times 3. Remember, at A2, which we found up above, was negative A0 over 2 times 1. That means that this would be negative A0 over 2 times 1 times 1 over 4 times 3, which, of course, I could rewrite that as 4 times 3 times 2 times 1, so 4 factorial. And also we had a negative there, which makes this a positive A0 over 4 factorial. If I go back to the previous one then, seeing that I got a factorial, let's write 2 times 1 as 2 factorial, just again to illustrate the pattern. Let's do one more. Let's do A6. A6, in this case, I would see that n will be equal to 4, comparing A6 with AN plus 2. That would then give me negative A4 over 6 times 5. Then replacing A4 with A0 over 4 factorial, we get negative, so A0 over 6 times 5 times 4 factorial, which would be negative A0 over 6 factorial. And I think this gives us enough indication for what the general pattern is going to be. And that's kind of one of the benefits of doing a pattern recognition here, is I don't have to compute infinitely many terms. I can see, I can make an educated guess as to what the A8, A10, A12 terms would be. Well, here we go. What would A2n be? So in other words, the formula for the coefficients for the odd terms. Well, if I look at this pattern, there's really kind of 3 components to this. The numerator is always A0. Okay. Notice that the denominator is always the factorial of the subscript. In other words, this is going to be, if the subscript is 2n, that's going to be 2n factorial. Also notice that I have an alternating pattern for positive and negative. Negative, positive, negative. So I'm going to have a factor of -1, but that's going to be to an exponent. Let's see if we can figure out what that exponent is going to be. Well, in the case for A2, it was negative. A4, it was positive. Now let's look at the subscripts here. The subscript on this is 2 times 1. The subscript here is 2 times 2. The subscript here is 2 times 3. And notice that this one is negative, this one is positive, this one is negative. Also notice that the factor of 2 is odd, even, odd. In other words, it's going to be negative 1 to the nth power is going to be the coefficient for the the even terms. Okay, and now let's look at the even coefficients. So n even. Again, we have to start somewhere, and the smallest index value for the odds would be 1. So therefore, what I'm going to do is I'm going to say a1 is not equal to 0. So that's going to be my starting value. Okay, it's a very similar story to what we did over here. If a1 is not 0, we can then generate a3. Of course, if it was 0, then a3 would be 0. But using this recursion relation, we can come up with 2 terms later. So in other words, a3. All right, a3 using sort of the same argument that I did over here. If the subscript is 3, then that means that in this case, using this formula, n is equal to 1. Now, if I go over to here, that's going to be negative a1 over, so n plus 2, that means 3 times 2. Of course, 3 times 2 is the same as 3 times 2 times 1, which means, and then the fact over here that I had factorials, I'm going to just write that as a factorial. So negative a1 over 3 factorial. Now for 2 terms later, let's say a5. What would the n value be? Well, if the subscript is 5, the general subscript is n plus 2. That means that I would have n is equal to 3. In other words, I'm going to use the previous term within this formulation. I would get negative a3 over, well, if n is 3, that's going to be 5 times 4. I go ahead and replace a3 with what I found in the previous line, and notice this is negative times negative, which of course makes that just an a1, and then on the bottom I'd have 5 times 4 times 3 factorial, which would be 5 factorial. Now we could generate another term or two, but we see that the same pattern is going to apply, where I'm going to have the numerator is this initial, the first of the even, I wrote this as odd, whoops, that should be even. And I wrote this as even, and that should be odd. Okay, so I have all of the odd coefficients here, and we can see that in general, what would a 2n plus 1 be? Well, I know that the numerator is going to be a1. I know that the denominator is going to be the factorial of the subscript, and I'm going to have a power of negative 1 to something. Well, let's see what that something is going to be. Notice that in this case, the subscript, so in other words, if it has the form, say, 2n plus 1, so this would be 2 times 1 plus 1. This would be 2 times 2 plus 1, right? That's 3, that's 5, so on and so forth. And this one is negative, this one is positive. So what happens is I take the coefficient of 2, or the factor of 2, as my exponent on negative 1. Negative 1 to the first, negative 1 to the second, so on and so forth, meaning this would be negative 1 to the n. And these would be the formulas for the coefficients for the even terms and the odd terms. Now let's look at the general solution. Okay. So remember that the series was y is equal to the summation from n equals 0 to infinity a sub n x to the n. Okay, so that was the series that we had started with. Now let's go ahead and write out a handful of terms here. And I'm just going to do it sort of in the general expansion here. A naught x to the 0, which would just be a naught, plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th, and etc. Now if I go ahead and fill in the coefficients from the formulas, a naught, so this is the even term, that would be oh, that's just the unknown, the a naught that we assumed was non-zero, plus a1x, plus, now we're going to start using the formulas over here. A2, well, that's going to be a naught, negative 1 to the n, so in other words, that's going to be negative a naught over 2 factorial x squared. A3, that's going to be, well, I could just use this right here because I have it listed. That would be negative a1 over 3 factorial x cubed plus, let's do another one, a4, which would be a naught over 4 factorial. A4 means that that's 2 times 2, so in other words, the n value is 2, meaning it's negative 1 squared, so it's positive, and then x to the 4th, and of course, so on and so forth. Now, let's take this series, which since it's convergent, I can rearrange the terms, and let's combine all of the even powers and all of the odd powers. I would get a naught plus, minus a naught over 2 factorial x squared plus a naught over 4 factorial x to the 4th plus all the higher order even terms, and then plus a1x minus a1 over 3 factorial x cubed, and then following the pattern, I would get plus a1 over 5 factorial x to the 5th plus ... again, higher order terms. And let's see what happens when we analyze those two strings of terms. Notice that this first string here, if I factor the a naught out, this is actually equal to a naught times the cosine of x. Plus, now if I take the string of odd power terms, factor out the a1, I get a1 times the power series of the sine function, telling me that the general solution is a naught cosine plus a1 sine. Now, of course, this doesn't always happen for series solutions, which is the power of series solutions, that if my my solutions are much more complicated than the elementary functions, we might just have an infinite series. But in this particular case, we get a linear combination of the sine and the cosine. If you go back to the original differential equation I started with, remember that was y double prime plus y equal to 0. What we're looking for is what functions have the property that when I take the function and I add to it its second derivative, they cancel out. Well, certainly sine and cosine fit the bill, right? Because the derivative of sine is cosine, but then the derivative of cosine is negative sine. So negative sine plus sine would be 0. Same thing with the cosine. When I add its second derivative to itself, they do cancel out. Okay. Thank you for watching, and please consider subscribing.